Okay, so we continue with this next few exercises. This next one has a finite dimensional vector space V and a homomorphism T from V into itself, which is not onto. We have to prove that there is a non-zero vector in the vector space at which if you evaluate T, you will get 0. So let's see how we can do this. Note that T is a homomorphism from V into V, and V is finite dimensional. So, and also it's given that T is not onto. So that means T also cannot be 1-to-1, because we have already come across one exercise, no? Exercise 5. By exercise 5, if you have a homomorphism like this, which is 1-to-1, then it also has to be onto. But since it's now given that T is not onto, so T cannot be 1-to-1 also. So we write that conclusion like this: since V is finite dimensional and T is not onto, it follows from exercise 5 that T is not 1-to-1 as well. So being not 1-to-1 means what? We of course know what being not 1-to-1 means, but it also means, apart from the regular meaning, that the kernel of this homomorphism T is non-trivial, is a non-trivial subspace of V. And what that means is that there is at least one vector in that kernel which is different from 0. So there exists a vector V not equal to 0 in the kernel of T. Bugs have come inside. Anyway, so now the fact that this vector V is coming from the kernel of T just tells us that this will happen. If you evaluate T at V, you are going to get the 0 vector. And we have Vt equal to 0. That means on a finite dimensional vector space, if we have a homomorphism like this type of homomorphisms have a name. They are called linear operators. So if a linear operator on a finite dimensional vector space is not onto, then it will be, it will take the value 0 at a non-zero vector. Next, exercise 10. Let f be a, okay, so this is the next one. Let f be a field and let fx be the polynomials in x over f, which of course we already know forms the vector space over f, the space of polynomials. Prove that fx is not finite dimensional. That means fx cannot have a finite basis over f. No finite set of vectors from fx, that is no finite set of polynomials, can generate the entire space fx. Consider the set S, which is the set of all monomials, that is all the powers of x. Okay. Now the first thing we will show is that this set is linearly independent. Linearly independent means not linearly dependent by definition, which means that if you choose any finitely many vectors from this set, then a linear combination of those vectors will be 0 if and only if the coefficients in that linear combination are 0. And that is what we are now going to show. For any positive, or okay, let us write like this. I cannot write it in a nice way in only one sentence. Let n be a positive integer for distinct non-negative integers I1, I2, etc., In, and scalars, an equal number of scalars, which are of course coming from the field F. Let this linear combination plus alpha 2x I2 etc. plus alpha n x In be equal to 0. So now you can understand why we are writing these things. These monomials, that is x to the power I1, x to the power I2, all the way up to x to the power In, these are some elements taken from the set S. To make them distinct, we have taken this I1, I2, this Ij's to be distinct exponents. But to allow for the possibility that one of them may in fact be 1, that is one of these monomials may be 1, we have allowed them to be non-negative integers, not just positive integers. Also, we are taking all of them to be distinct. So if at all one of them becomes 0, the others of course then have to be positive because they are all distinct. And we have now here taken a linear combination of these monomials and we are setting it equal to 0. Now we want to prove that all the alpha i's are 0 or all the alpha j's are 0 because we already have an I here now. Now look at this expression. The left hand side is just simply a polynomial in x, where these monomials are in fact distinct terms. It's like writing a polynomial like this: 1 plus 3 x cubed minus 2x to the power 10 plus 5 say x to the power 100 equal to 0. These monomials, one of them is 1, the other is x cubed, x to the power 10, x to the power 100. These are all distinct. So the expression on the left hand side of this equation is itself just a usual polynomial in x. Now by the definition of equality of two polynomials, the right hand side is also a polynomial, which is the 0 polynomial. So by the definition of equality, the coefficients must be 0. In this case, of course, this will not happen. I am just simply giving an example. Strictly speaking, what I have written here is entirely false, because if you treat these coefficients as real numbers, then this polynomial is never 0, but I am just simply describing the situation here. So that means just from this equation we can directly say that all the coefficients in fact now will be 0, and that fact actually depends on the fact that these monomials are distinct by the definition of equality of two polynomials, or you can also write like this: equality in the vector space fx, all the alphas are now going to be 0. Hence, non-trivial linear combination of monomials will never give us 0. Only the trivial linear combination gives us 0, where all the coefficients are 0, and that means just one thing, that the set S is linearly independent. Hence, S is linearly independent. Okay. Okay, now what is the consequence of S being linearly independent? Recall a previous result where we proved that if a vector space has dimension n, where n is a positive integer. Actually n can be 0 also, but just simply I am saying, if a vector space has dimension n, then the size of a linearly independent set in that space can be at most n. It cannot be larger than n. Now here we have obtained a linearly independent set whose size actually is infinite, because S is an infinite set. So the vector space cannot possibly be finite dimensional, and that's why it is not finite dimensional. So that's the conclusion we are now going to write, and that in fact will complete the solution. But we need to mention that result which we will use here. Since S is infinite, what was the it's lemma 4 to 4. Lemma 4 to 4 makes us conclude that fx is not finite dimensional, and that's just it. That's what we wanted to show. Man, it's so hot here. Just give me a moment. In this part of the world, it's unbearably hot, and especially in this place, not just the heat but humidity is making it even worse, much worse than the actual heat. Okay, so next, exercise 11. Let a set is given Vn, which you will see is the subset of this fx, the polynomial space. It is the set of all polynomials px such that the degree of px is less than n. Define T by this formula: alpha naught plus alpha 1x plus alpha n minus 1 to the power n minus 1 t is defined to be equal to alpha naught plus, so we are replacing all the x with x plus 1 plus alpha n minus 1 x plus 1 to the power n minus 1. Okay, so you can that we have to prove. You cannot just simply see. Prove that T is an isomorphism of V onto itself. Is an isomorphism noun of Bn onto itself. Now there is a problem with this exercise. You see, we have been given a subset of fx. Fine. There is no problem with the definition of this subset. And then a function t has been defined with this subset as domain and with fx of course as codomain, if you want to call the second set a codomain, which looks like this. Now we are being asked to prove that this function t is in fact an isomorphism of Vn onto itself, which actually, I mean, this statement has in it the claim also that this Vn in fact is itself a vector space, and in fact it's a subspace of fx, and that is actually not true. There lies the problem. Do you want to see why it is not true? You see, you look at the definition of Vn. Vn consists of all polynomials Px whose degrees are less than n, where n of course we can understand is some non-negative integer. Now say your n is 3, then we are considering all polynomials in fx whose degrees are less than or equal to 2, that is the degrees do not reach 3. So either we have polynomials of degree 0 or not either or, we have in V3 all the polynomials in fx that are of degree 0 as well as all the polynomials which are of degree 1, that is linear polynomials, as well as all the quadratic polynomials. But among all these polynomials there is one polynomial which in fact does not appear in V3 if the definition of V3 is just this, and that is the 0 polynomial. And that is because this statement is not wrong, but in fact it is meaningless. Degree of the 0 polynomial has not been defined in this text. Some people define it to be minus infinity, some people define it to be minus 1, but that has not been done in this text. So V3 will in fact have all the polynomials whose degrees are less than or equal to 2 except the 0 polynomial. So if V3 does not have the additive identity or the 0 vector of our fx, how can it be a subspace? So that problem is there. And in fact you can also see one particular case where things look extremely if you take n equal to 0, okay, if you take n equal to 0, then according to the definition of this, since the degree of every polynomial is by definition a non-negative integer, no degree will be less than 0, because we don't have negative degrees. The way we have defined degrees, the degrees are always non-negative integers. So that means V0 or V0 is actually the empty set, and the empty set of course is not a subspace of fx. So to rectify this problem, we of course have to separately supply 0 to Vn. In fact, we mentioned this also in the solution. We mention this, we make the requisite modification to Vn, and then only we proceed. Note that Vn is not a subspace of fx, since 0 does not belong to Vn. We have not defined any degree for the zero polynomial over f. If one actually defines it, then there is no problem. With that extended degree definition, this will then again become a subspace, but we don't have that now. So instead of Vn, we consider Un, which is Vn union 0. 0 is not there, so we consider 0 as an extra thing, and Un will now be a subspace. It's straightforward to show that Un is a subspace of Fx, and straightforward to show means it's left to you. It's extremely easy. You just now you don't even have to see whether Un is a non-empty subset or not. It is non-empty because now the zero vector is there, zero polynomial. So what you do to show that Un is a subspace, you take two polynomials from Un and you take two scalars, you form the linear combination, show that it is again in Un. So that part is left to you. It's extremely easy. Some cases will arise depending on whether those two polynomials that you choose, whether one of them is 0 or not, or whether both of them are 0 or both of them are non-zero, that is, they are actually coming from Vn. So some cases will arise, but you can of course easily handle all of them. So this part is left to you, and in fact the t that we have defined in the exercise actually has been defined on Un, because you see we have considered the input of that t to be a polynomial which looks like this, and this is precisely what all the elements in Un will look like, because their degrees can be at most n minus 1. If at least one of these alpha i's is non-zero, then the polynomial has a degree, that is, it's a non-zero polynomial, and that degree from the look of this polynomial is less than or equal to n minus 1. And in that single case where all the alpha i's are 0, it is the zero polynomial. So either the degrees are less than or equal to n minus 1, that means strictly less than n, or it is the zero polynomial. Okay, so the general element, the typical element of Un looks like this. Okay. So now first of all we need to show that this T actually maps any element of Un again to an element of Un. That's the first thing. Straightforward to show that Un is a subspace of Fx. Our function T is in fact a function with domain Un. Okay. For any element in UN, we have let us first once again write down what T does to this element. T takes this element to this element. Is it the thing, or yes, it is the thing? Because I every now and then make silly mistakes now, so I'm making sure it's all right. Okay. Now, looking at this polynomial, you can see that it's actually a polynomial in x. The other higher powers of x plus 1, you can in fact expand all of them using your usual binomial theorem, which is true in this setup also. In fact, the binomial theorem is true in any commutative ring. A version of the binomial theorem that we usually have in the system of real numbers or complex numbers, that is true in any commutative ring. In fact, while we were going through ring theory, at one stage I mentioned this also. So, using binomial theorem, we can expand all these powers. This one, of course, needs no expansion. And after expanding and collecting like terms, you can clearly see that it is going to be again a polynomial in x, and that too a polynomial whose degree is at most n minus 1, because the highest degree term, of course, will come from this expansion. I mean the expansion of this last power of x plus 1. It may happen that alpha n minus 1 is actually 0, but I am saying the highest degree, highest possible degree term can come from this term. If alpha n minus 1 is 0, then lower degree terms will appear. If alpha n minus 1 is non-zero, then the degree of this polynomial will actually be equal to n minus 1. Because when you expand this using binomial theorem, you will get the term x to the power n minus 1 plus then your usual formula. Other lower degree terms of x will appear. So that means in any case, the degree of this polynomial is at most n minus 1 or the polynomial is 0, which is the case, of course, when all the alphas are 0. And what does that tell us? That just simply tells us that this output in fact is in UN. Clearly, this, in fact, we write output. From the context, we know what output means. This output is either the zero polynomial or is a polynomial having degree at most n minus 1. i.e., in other words, the output belongs to un. So we now know that at least t is a function from un to un. Next, of course, we have to show that t is a vector space homomorphism. So for that, let we can just simply continue to write like this: beta naught plus beta 1 x etc. plus beta n minus 1 x to the power n minus 1 plus belong to un, and say alpha belongs to f. Then first usual thing, we need to prove that t respects addition. So we add these two polynomials. And on their sum we apply t. So first we rearrange the things. Okay, I should not have said rearranged, but by the definition of addition itself, we have this. T. So this will be what? In place of x, we have to put x plus 1. Beta 1 plus gamma 1 x plus 1 . Just now I said something, did you notice? I was saying that after this, in this step, rearranging the terms, we can write like this. Actually, that is not wrong. We can interpret this sum in that form also. First of all, when we have the polynomials, there you have a sum, and I am not talking about the vector space structure. Thinking of polynomials as a ring. Ring sum and vector space sum actually are the same, simply summation, addition of two polynomials. So when you first add polynomials, there is a set definition. According to that definition, you have to add beta naught and gamma naught, and then you have to add beta 1 and gamma 1 and write like this, because when you are defining addition, that time these are just some formal symbols, but after you have defined addition as well as multiplication and did everything in that ring of polynomials fx, then what you do, you identify the polynomials, the monomials themselves as some polynomials. For example, the monomial x, just that symbol x, actually itself is a polynomial where only the coefficient of x is 1, the multiplicative identity of your field, and the other coefficients are 0. With that identification, the monomials themselves become elements in fx. Then if one applies the definition of multiplication and addition, one will see that just treating this or just interpreting this polynomial, for example, as a formal symbol, it is the same as interpreting this as an expression in fx, where x is a single polynomial. This beta 1, beta naught, these are also polynomials. Beta n minus 1 x to the power n minus 1 is actually x multiplied n minus 1 times. Then you get the same polynomial. If one evaluates that expression using the definitions of addition and multiplication, then one gets that same polynomial. So what I am trying to say here is that these formal expressions, of course, are the things with which we start when we define a polynomial ring. But after we have defined everything, the operations and everything, then the formal expressions themselves have a second interpretation in which these intermediate multiplication, addition, these actually become the addition and multiplication that you have in the ring. So there are in fact two interpretations for this polynomial symbol, and they in fact give us exactly the same result. So if one wants, one can just simply treat these polynomials like how we normally treat them. For example, beta naught plus beta 1 x means actually the sum of these two polynomials. So in that sense, I was saying rearranging them, we get this. But now of course we continue our calculation. Plus the intermediate terms, of course, are there. Beta n minus 1 plus gamma n minus 1 because if you see, if you don't have that interpretation, then this expression becomes meaningless, no? Or at least you will at first get confused if you look at this expression. It looks like a polynomial in x plus 1, but it of course also is a polynomial after all in x once one expands these powers of x plus 1. So you can just simply see that treating these things, this entire thing, as a polynomial in x, using the usual rules in the polynomial ring fx, we can write this polynomial as gamma 1 x plus 1 plus and in writing this step we have used the distributive law that we have in the polynomial ring fx, and this is nothing but the first one is simply the t image of this polynomial, and the second one is the t image of the other polynomial. Most of these calculations look quite big, but they are standard routine straightforward calculations. So this means that t in fact respects addition on un. Also Now, does T respect scalar multiplication? If you multiply this polynomial by this scalar, say n minus 1 x to the power n minus 1, I don't have space. Without blabbering too much about what is going on, you already know. I'm just simply going on writing the thing. By the definition of T, again this is just simply T. So T also respects scalar multiplication. That means T is a linear transformation, I mean a homomorphism. Hence T is a homomorphism. Now we are left to show that T is one-to-one and onto, but luckily we don't have to do both of them, because T is a function from un to un, and un in fact is itself a finite dimensional vector space. So it's enough to show that T is onto, because what is that exercise? Is it exercise or yeah, exercise 6. If you have a homomorphism T from a finite dimensional vector space to itself, which is onto, then it is also automatically one-to-one, and hence it will be an isomorphism. So we write like this. Now, since T maps un into itself and un is finite dimensional, and the reason for that is this. In fact, un is the linear span of these vectors, Why am I putting full stop? It's not over yet. And U is finite dimensional, it's enough to show that T is onto, because then it would automatically be 1 to 1. By, we did not mention it now, by exercise 6. So now we want to show that T is onto. So let us take something else. Let delta naught plus delta 1x etc. plus this belong to un. Then we want to show that this is the T image of something, again in un, that something is in un. We can write x as x plus 1 minus 1. Just like that, this one as x plus 1 minus 1 n minus 1. Okay. Now expanding the powers of x plus 1 in the above, no, not just x plus 1, x plus 1 minus 1 in fact. Powers of x plus 1 minus 1 in the above expression using the binomial theorem or binomial formula and rearranging terms. More specifically, you can, of course, in more detail, if you want to write, you can write, instead of rearranging terms, you can write collecting like powers of x plus 1, like that. But you already know what we mean here, so I am not elaborating any further on this. Rearranging terms, we obtain this. as a linear combination of these. Okay, so that means what? It just simply means that un itself is equal to the linear span of these powers of x plus 1. That's what it means. So we want to mean this. un is the linear span of this set and now if you go back to the definition of the function t, you see that in fact every image okay, now I am going to write something, you see whether you understand it or not. So this implies t is onto. If we were a little confused about this sudden conclusion, it is just simply this. See what we have shown here. We have shown here that un looks like this. That means every element in un is ultimately a linear combination of this. So this element, for example, in un that we have chosen, this element will be some linear combination, say lambda 1 plus lambda, or we start with 0, lambda 1 x plus 1 plus this. Any element in un will in fact look like this, but where the lambda is are of course coming from f, but this is equal to the t image of this polynomial. And this polynomial is also in un, and that is why t is onto. Instead of writing all these things, I have just simply written like this, which you can understand. Someone may blame me that I am not writing all the details, but sometimes it's okay. What a predicament. Heat, humidity, and to make matters worse, I have that skin allergy also. I am allergic to light, so I have to dress up like this, covering up everything as much as possible. So this is like a literal hell. So that's what we wanted to show. Now that we have shown t is onto, so that's it. So automatically t will also be 1 to 1, and hence it will be an isomorphism of un onto un. Now before we proceed, let me just use some more ink. Next, 12th, let again another set is being defined, W now this time the author is not using degree, so now there is no problem with this new set belonging to fx, such that not just that this is how a general element in un looks like, we have already seen, but now there is an additional condition. So this W will turn out to be a subset of un, and that condition is this, that the sum of all these scalars is 0. Show that W is a subspace of Vn. No, actually that is not true, because Vn itself is not a vector space. So in the exercise itself we will modify it slightly. Show that is a subspace of Vn union 0. If you want, you can write un also here, but if you suddenly look at this exercise and forget about the previous one, then un may confuse you, because there is no un. I mean, what is un? So instead we write like this, and find a basis of W over F. Okay, so we have understood the situation. First of all, we need to show that W is a subspace of Vn union, this vector space, and that I am going to leave to you, because it's also quite straightforward. It's let us, however, still just briefly see what this requires us to do. Of course, this will demand that W is, first of all, it be non-empty as a subset of Vn union 0. It is non-empty again. The 0 polynomial where all these alpha i's are 0 belongs to W, because their sum, which all of them are 0, is of course 0. So W contains the 0 vector, or the same thing, the 0 polynomial. So W is a non-zero subset of this vector space. Then you take any two, then the usual procedure, you take two vectors from W, you take one scalar and show that the sum of those two vectors and the product of any one of them and that scalar, all of these things are again in W. So you have to work with this condition, and that's how you can show that this is a subspace. Okay, now we come to the other part. We now need to find a basis of W over F. Now when generally you you are faced with the task of finding a basis for a subspace. What you do, you take an arbitrary vector in that subspace and then try to see what are the vectors that are spanning that subspace. Of course, there are multiple sets of vectors that can span that subspace, but from those sets you have to remove unnecessary vectors. You will realize what we are talking about here when we run that process here. Now let this belonging to W be any element. Okay. Now this is how a general element in UN looks like, or in this space looks like, but there is this additional condition. Then this is equal to 0. Now looking at this polynomial, it just simply tells us this simple fact that these monomials, these vectors span this polynomial. But keep in mind, you need to find a set of vectors in W which spans W. Note that none of these vectors are actually in W. That is the strange thing here. Why? Because you see, x to the power n minus 1 of course is again a polynomial that looks like this, where alpha n minus 1 is 1 and all the lower suffixed alphas are 0. But if you add all the alphas, do you get 0? No, because one of them is non-zero and the other previous ones are 0. So the sum is 1, it is not 0. So none of these things are actually in W. And that's why we should just simply not look at how this polynomial just looks, and instead also use this condition. So now using that condition will look like this. Because of this equation, in place of alpha naught we can write this. Other intermediate terms are also possibly there. Now rearranging things, we get this. X minus 1, etc. I mean, if we decided to write one more, then we would have here minus alpha 2, and here we would have alpha 2 x square. So let's just write that, otherwise it looks too barren. And what about this one? Alpha n minus 1 x to the power n minus 1 minus 1. Now look at this other, these are not monomials of course. These polynomials however belong to W, because if you add their coefficients, one of them is 1 and the other is minus 1, you are actually getting 0. And also all of them are of this form. None of them in fact uses any monomial where x to the power that superfix is greater than n minus 1, where now we can say, because of all of this, that these vectors in fact span W. So despite how the definition of W looks, in fact the spanning vectors, I should not say these spanning vectors, but these vectors that span W are hiding inside. There may be other spanning sets also, but we don't care. We have found one, and in fact it will turn out to not just be a spanning set, but it will now show that it's a basis. Hence W equals the linear span of these vectors. Next, let lambda 1, we can take 1 here because things are starting with 1 now. Lambda n minus 1 belonging to F P scalars such that lambda 1 times x minus 1 plus lambda 2 times x square minus 1, which is there somewhere, I mean just after this, and this is equal to 0. Our aim now is to, of course, prove that all the lambda i's are 0. This means, okay, now we can of course write this same equation also like this, minus lambda 1. So whatever we did here, we are now doing the back calculation. Plus now in this form you have this polynomial on the left side of this equation as a polynomial in x, that is in fact a linear combination of these monomials 1, x, x square, etc. up to x to the power n minus 1, which however are known to be linearly independent. In fact in that exercise itself we showed that the set S consisting of all monomials is linearly independent. Since are linearly independent, so all these coefficients, the coefficient of 1 here is this, they are going to be 0. This equation however we will have no use of. These ones in fact tell us what we need, that all the lambda i's are 0. Thus the polynomials So they span W and also they are linearly independent, so they form a basis of W. Hence, and that's just it. That is the solution. Next, let V1 V2 through Vn be a basis of V, some vector space, and W1, W2, etc. to Wn be any n elements in V. We are going to define a function again from V to V. Define T on V by this formula. Lambda and V and T. There is in fact no need to write it in one line. Show that T is the homomorphism of V into itself. There are two parts. Part A, show that T is a homomorphism of V into itself. That is part A. And part B. When is T an isomorphism? The first one is absolutely straightforward. Please do it yourself. You can pretty much understand what you know what you have to do. You take two vectors like this, which are, of course, both of them are linear combinations of these VI's. You add them up, apply T on that sum, and you see that that equals the sum of the T values of the individual vectors, applying this definition. Extremely straightforward. And you also show that when you multiply this by that is T respects scalar multiplication. So that's how you show that T is a homomorphism of V into itself. Into itself, of course, because the Wi's are also coming from V. So these outputs are again in V. And there is no question about the well-definedness of T. Oh, but there is a question. You see, uh, you have to in fact show that T is well defined. That is because just simply looking at the definition, we may not at once guess that T is well defined. To prove that T is well defined, you have to prove that for a given input, this output is only one output, that is, it's a unique output. For that, like this, you consider two vectors which are in fact equal input, say mu1 v1, mu_n vn. You prove that their t values are also equal, and in proving this, the fact that these vi's form a basis of v, that fact will be used. In fact, without it, and particularly linear independence of the vi's implies that t is well defined. That has to be used. This, however, I entirely leave to you. Based on your experience so far with these things, you should be able to do this. Anyway, if you have some doubt or if you fail to come up with the actual proof, you please let me know. When is T an isomorphism? Okay, T is an isomorphism assuming that we have already proved it's a homomorphism. T is an isomorphism if and only if its kernel is the zero subspace of V. Okay, now kernel becoming the zero subspace of V means what? Let's just think about it for a moment. If this is your input, then this is your output. Now, for this input to be in the kernel, this output must be 0. So that means the entire thing now boils down to this linear combination becoming 0. So a linear combination of the wi's is 0 for some particular scalars. Now that actually can happen, of course, in several ways. If the wi's are linearly dependent, then it can happen in several ways. But if the wi's are linearly independent, then there is only one way for this linear combination to be 0, and that is precisely when all the coefficients are 0. There is no other way for this linear combination to be 0 if the wi's are linearly independent. And that means what? That would mean that in the kernel only the 0 vector will be there. Kernel is 0. Now assume that, let's see what happens if the wi's are not linearly independent, that is, they are linearly dependent. Assume that these are linearly dependent, then there exist scalars, say nu1, nu2, nu_n belonging to F, not all 0, this is important. Such that this linear combination is equal to 0. Okay, but then what about the corresponding linear combination of the VI's? And okay, so that means if the Wi's are linearly dependent, then the kernel of T has a non-zero vector. By the way, how are we concluding that this vector is non-zero? That is because the VI's form a basis of our original space V, right? So the VI's are linearly independent. Now the fact that not all new i's are 0 makes this linear combination of the VI's a non-trivial linear combination. Now linear independence of the VI's implies that only the trivial linear combination of them can become 0, where all the scalars are 0. Here, however, at least one scalar, at least one new I is non-zero, so this cannot be 0. So that means if we want, so what is it that we have proved here? If the Wi's are linearly dependent, then the kernel of T has a non-zero vector. That means T is not an isomorphism. Of course, equivalently, if T is an isomorphism, then the kernel of, the Wi's should be linearly independent. Let's just write the conclusion. We have thus shown that if this set is linearly dependent, then the kernel of T is not this, and so T is not 1-to-1, and hence it's not an isomorphism. Equivalently, if T is an isomorphism, then this is linearly independent, and you can prove that the converse is also true, that when these are linearly independent, then T has to be an isomorphism, which is in fact rather easy. You just assume that they are linearly independent. You take any vector in the kernel of T you will see that that vector has to be 0. That part I leave to you. Conversely, show that if this set is, you may not decide to write it as a set, you may just list the vectors, then in place of each you have to write are linearly independent then T is an isomorphism. So that's the W becoming linearly independent is a necessary and sufficient condition for T to be an isomorphism. Okay, we have done 13, 14, 15, 16. Let's just complete this set of exercises. Not many more are left, 4 more are left, and we will not in fact get to solve all of them. You will see why. For now we have to content ourselves with some mere mentions of some facts which we will see later on when the time comes in these next solutions. That's why I am saying that let us finish. We have to complete these elementary things and then we have to go to higher things. Show that any homomorphism of V into itself when V is finite dimensional can be realized as in exercise 13. Okay. Can be realized as in exercise 13 by choosing appropriate elements. So that means in the previous exercise what we showed is that if we have a finite dimensional vector space where the basis of course is there, and if we take any W-wise an equal number of any vectors in the vector space, then we can define a linear transformation like that. Now here we have to show that actually every linear transformation on such a vector space will look like that previously for some W-wise, provided the space is finite dimensional. Since V is finite dimensional, it has a finite basis okay. Let T be, now we cannot define T. T is any homomorphism. Dang it, man. Any homomorphism of V into itself for an arbitrary element V belonging to P. We know because there is a basis, there exist unique scalars, say lambda 1, lambda 2, etc., belonging to F, such that V is the corresponding linear combination of these VI's. Then what is VT? VT is this now, because T is a homomorphism, by the definition of a homomorphism, this T image will be this linear combination of these individual T images. So the W's that we have here can be taken as just these vectors. Now take W1 to be the image of V1 under T and so on. And that's just it. So in this case, it turns out that those are the W's. And note that the W's in fact are fixed. I mean, for a given basis, the W's are fixed and they do not change as the vector itself changes. When the vector changes, only the scalars change. But these VI's, of course, are staying as VI's, so their images under T also stay fixed. So this is the 14th one. Again, return, okay. Herstein cannot seem to leave this exercise 13. Returning to exercise 13. Now this is something that I will just simply, I won't write any solution, but I will argue to think about this. Since this is a basis of V, it was already given. Each VI in fact No, not each vi, sorry, each wi. Those wi's themselves, each one of them is expressible as a linear combination of basis elements. That's what a basis does. It generates the whole space is a linear combination of these vi's, alpha I n vn, where the alpha i's of course are coming from the field of scalars. Show that the n square elements belonging to F determine the homomorphism T. And for as a I should not actually write solution, but as a hint to the solution, see the third section of the 6th chapter, section 6.3. Many of you already know what these alpha i's are. They are the entries of an n by n matrix, and in fact this association between vector space homomorphisms of a vector space into itself and square matrices in fact is something that tells us that in a sense linear operators and matrices are actually the same thing. Matrices of course find their way into almost everything, particularly in the early formulation of quantum mechanics. Things were formulated in terms of matrices, but later people of course used operators. But matrices are extremely useful. We will see these things. Now the actual exercise that these alpha i's in fact determine the homomorphism completely, and in fact they tell us exactly what needs to be said about T. In fact what that actually means is this: if T is given and a fixed basis is given, then these alpha i's are uniquely determined in this sense, which of course is not anything surprising, which you can simply see from the situation. And the uniqueness of these alpha i's come from the fact that we have a basis, and so these alpha i's are appearing as scalars in the expression of these wi's as in these expressions expressing wi's as linear combinations of basis elements. So linear independence of the vi's makes sure that these alpha i's are unique. But if some alpha i's are given in F, some n square scalars are given in F, and one defines these wi's, in this manner, then using those wi's you can define a function T just like what we did in exercise 13. And this association actually tells us that these alpha i's in fact are what we need to define T completely. That's what this exercise means. Anyway, all these things seems somewhat vague, and they are. The exact association can be seen here. If you want, you can go to this section and see for yourself, or we can wait. And there is another one. similar. If the dimension of the vector space V over the field F is n, if V is an n-dimensional vector space, then prove that this is n square. About this I will just simply say that it has already, if the proof is already there in this result, recall that this is the set of all vector space homomorphisms from V into itself, and we have already seen that this set itself becomes a vector space over that same field F under a naturally defined addition and scalar multiplication. If the original space V is finite dimensional and that dimension is n, then the dimension of this space is n square. Exactly why this is n square, that you are supposed to guess from your understanding of this thing. Okay, anyway, I leave this entirely. I am not even going to say how one gets n square elements here which form a basis of this home space, homomorphism space. And finally, we have exercise 70. If V is finite dimensional, and W is a subspace of V, prove that there is a subspace W1 of V. Regarding this association between linear operators and matrices, there is a Wikipedia page, I think it's called Heisenberg's entry into matrix mechanics or something like that, where he realized that to explain the lines in hydrogen spectrum, he had to do something which matches with, only later on it was realized that he came across a product where PQ is not equal to QP. It was later found out that that product matches with matrix multiplication. So that's how people got an idea of using matrices to explain things in quantum mechanics, early quantum mechanics. I don't know the details, I am not a physicist, so but you can read that and you may find it somewhat amazing and motivating also. There is a subspace W1 of V such that V is the direct sum of W and W1. This one also, I will write a solution, but it will be sketchy. I will leave some details to you. If your original subspace W is the zero subspace, then we can take W1 to be V itself. What that means is that in this particular case, V is equal to V plus 0 plus V. Keep in mind, you have to show this, no matter how trivial it looks. Okay, so those are the things that I am leaving to you. And there is another extreme case. If your original subspace is actually the entire space, you can guess what we are going to write here. Then we can take W1 to be the zero subspace. So now that these extreme cases are out of the way, we can come to the usual W's. Now let W be different from both the zero space and the entire space V, since V is finite dimensional so is W, being a subspace of V. In fact, its dimension will be less than the dimension of W, because see, W is no longer equal to V, and also the dimension of W is not at the same time 0, because W is not equal to this also. And hence W will have a basis which is first of all non-empty, because W is not the zero space, so there will be something. Basis of W. Now we know from a previous result that a basis of a subspace can be blown up to form a basis of the entire space by putting some extra vectors into it. And what is that result? Lemma 4 to 5. By lemma 4 to 5, there exist vectors, some vectors in V such that this superset is a basis of V. Okay, so just like those two extreme cases, in this intermediate case also, you now have to prove this. Show that V is the direct sum of W and this subspace. That means this will be our W1, the linear span of these extra vectors. You have to actually show this. So that means this will be our W1. Let me just finish by saying that what do you need to show this? First of all, you have to show that every vector in V is a sum of two vectors. One of them is coming from W and the other is coming from this, which in fact will follow almost directly from the fact that this is a basis for the entire space V. So the part of the linear combination that has the W's, that will give you that part in W, and the part of the linear combination which has the V's, that will give you a vector here, and your original vector automatically will be a sum of those two vectors. And the fact that this sum is a direct sum then demands us to show that this expression of a vector as a sum of a vector from here and a vector from here is unique. That uniqueness also you have to show. So once you do that, everything is over. Okay, so with this I end, of course, this video. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. And today is Tuesday, so this coming Friday again we have, let's do calculus again. We are going through the extended definitions of trigonometric functions, so we will then see periodicity and other properties. So that being said, this is just all for tonight. See you on Friday with calculus. Until then, have fun with mathematics. So this is me, Lucifer, from A Mathematical Room. Have a nice night.